as an engineer, there are many situations where you can measure one variable very accurately and precisely, but you do not have a direct measurement of all the variables in your states. For example, let's suppose you're developing a new bioreactor, and you're trying to implement this new reactor, and you've implemented the right design such that you can measure the temperature inside your reactor very precisely and accurately as a function of time, for example. But you do not have a good measurement of the pressure downstream or the flow rate of your products downstream. And those are important variables that you as an engineer would like to know to optimize the design of your bioreactor. So what do you do in this situation where you have hidden variables that you would like to know about, like the flow rate and the pressure downstream, but you do not have access to that variable? Instead, you have access to a different measurable variable, like the temperature. So let's write down the states in your system, the measurements, and the dynamics. The state vector, z, the fancy script z that I've written here, with an underline, which means it's a vector. This state vector contains all of the variables inside your system. For example, temperature, pressure, flow rate, etc. Might be concentration of your products. Right? There's a list of all of the variables inside of your system that you would like access to in an ideal world. The dynamics of your system can be written in the following way, where we have some time rate of change of your states. So for example, z is a vector, so temperature might come here in one of the entries. So you have the time derivative of the temperature is going to be some function of your states and the independent variables like position, x, and time. So you could have d temperature, d time is some function of pressure, flow rate, temperature, concentration of your products, and position and time, right? That's generally what we write down in our conservation balances. The same is true for the time rate of change of your flow rate, the pressure, etc. So you can write down the dynamics in this way. This is what the system obeys. This is the mapping between your current time step z and your next time step z at time t plus 1. This is how you can advance your system to the next time step. Now, if you had this relationship on the right-hand side, you have a model for how your system advances and marches forward in time. But like I said, in engineering applications, your measurements, which I've labeled with y, are not necessarily the entire states in z. So there is another matrix, C, called the observation matrix, that will pick out the variables that you have direct access to. So for example, when I said earlier that you have measurements of the temperature, but you don't have measurements of the flow rate or the pressure downstream, then it would look like the following. Just like that. In this particular case, your measurement y is just a scalar variable of temperature. And we have a measurement of that, and your measurement matrix, C, would just be a row vector of 1, 0, 0 multiplied against your full state vector, script Z. So we have temperature, pressure, and volumetric flow rate. So you could do a linear algebra calculation, 1 times t plus 0 times p, 0 times v, and out comes the only measurement that you have, in this case, temperature. So if you were to have a measurement of your temperature and your pressure downstream, but you didn't know your flow rate, we can rewrite it in the following. All right, in this case, your C matrix, which is called the observation or measurement matrix, would be an actual matrix instead of just a row vector. In this case, you have a 1 here and then 1 in this entry as well, because now the things that you actually can measure in your bioreactor are both your temperature, which you would just obtain by 1 times t, 0 times p, 0 times v, and then that's your first entry of temperature t. The next entry of pressure, which is what you can also measure in this particular Example, you have 0 times t, 1 times p, 0 times v, and out comes your measurements of temperature and pressure. But like I said, the full state is what your dynamics depend on. Therefore, in this case, your flow rate v is a hidden variable that you don't have direct access to. You don't have measurements of that. And so now today's video is all about how do you obtain the dynamics to your system when you only have a partial measurement of your states. If I have measurements of only temperature or temperature and pressure as a function of time, and you have measurement data of that from your experiments, can you use those data to estimate what your unmeasured states are, your flow rate or your pressure, the states that you do not have direct access to or direct measurement of? Can you estimate those unobserved states or unmeasured states and try to come up with an evolution equation for your dynamics? And this kind of situation happens all of the time. And this technique of measuring a variable that you have access to, a partial space of your entire state vector, and you take measurements of that and use that measurement to come up with a model or some kind of control process, is called embedding. And embedding is incredibly important and powerful in developing models for complex systems, because for almost every complex system we can think about, you don't have measurements of all the states inside your system. You only have a partial measurement. And sometimes you have a very good spatial and temporal resolution measurement of those partial measurements. So the question is, can we harness that very valuable data that you have for the partial states to develop a model? And in fact, there was a very nice paper about 10 to 15 years ago where these authors over here considered a toy problem of a minimal model that exhibits chaos due to nonlinearity in coupled ordinary differential equations. So here we have a coupled system of 3 ODEs that depends on the dependent variables x, y, and z. They're each a function of time. So it's coupled ODE, and this is called the Lorentz attractor system. So in general, you have the outputs of x, y, and z. So those would be your states. So your script fancy z vector would contain x, y, and z. And the dynamics right here are these 3 equations right here. You can clearly see that I can write the left-hand side of here, so dx dt, dy dt, dz dt, into the left-hand side of this equation, so d script z, which contains x, y, z as a column vector, dt, is going to be equal to some function of these guys. Right? You can tell on the right-hand side, there's some kind of parameter sigma. Y is one of your dependent variables, minus x, which is another dependent variable, and then x rho minus z minus y, x times y minus beta, which is another variable parameter. It's a parameter in your model that's already specified. So beta and sigma and rho are all parameters. There are numbers that you put into this system of equation. And finally, you have a product of beta with z. And you can see that this is a nonlinear coupled ODE. It's nonlinear because you have products that look like x times y, x times z over here. And it's coupled because the differential equation for x depends on y, differential equation for y depends on x and z, and so on. So they're coupled and they're nonlinear. So now, if you initialize a system from some position x, y, and z, and let the system evolve according to this dynamics, right? This maps a particular state, x, y, and z, to the next time step on the left-hand side. That's exactly what this differential equation is doing, right? Those are your dynamics. So now I'm going to play this movie. It looks something like this. So that point shows you the time evolution of the solution to this differential equation. Now, what these authors showed, which was really cool, is that suppose you didn't have access or direct measurements of x, y, and z. Suppose you only had measurements of one of the variables, x. So that's exactly the situation right here. I said earlier in your bioreactor, you have the full states, T, P, and flow rate, but you only have measurements of one of your dependent variables of temperature. Same situation here. We have a very complicated nonlinear chaotic system. It's got butterfly wings, right? They kind of have chaos because you can't really predict when they switch between the two different lobes. And you don't have measurements of x, y, and z. You only have measurements of x. So this squiggly signal you see over here is just a projection of this butterfly manifold wing on to the x-axis. So suppose you only had measurements of these guys right here along x, but you didn't have measurements of y and z. Well, it turns out that you can actually take those measurements of x right here and take two measurements of x in time. So you take one measurement of x at the current time, you take another measurement of x in one time step ago and two time steps ago. So now the x embedded over two time histories becomes your new space. And it turns out if you plot those time histories of one of your measured variables of x in time and plot it in this way, it turns out that you can recapitulate all the salient features of the Lorentz attractor system, like the butterfly manifold, the Lyapunov exponent that tells you how seemingly small changes to the initial condition could result in very, very different outcomes and time trajectories in space. And you can capture all the really cool features and topologies of this Lorentz attractor system. Again, this is a toy system, but it's a really cool example how you can actually just take one of your variables, measure that very precisely, and uncover a lot of the physics and chemistry and biology of a system that is very complex. So that's what we're going to talk about today. How can you take measurements of one of your variables, develop a model, and think about what you can measure, what you can observe, and how you can develop better models. Okay, let's get started. Let's start on the concept of observability and embedding using a very simple high school physics example. Suppose we had a mass of some mass m attached to a spring with stiffness k attached to a wall. Okay? So the force balance for the system can be written like the following. So what we have is acceleration, m times a, is equal to all the sum of the forces, which in this case has drag coming from friction from the surrounding air, which I'm just going to take as a linearly proportional drag as a function of some drag resistance zeta times the velocity u. And finally, on the right-hand side, we have a spring force coming from the elastic restoration force from a harmonic Hookean spring. That's listed right here. So what we're measuring is the position of this mass x from some equilibrium position into the positive and negative direction. And it's got forces of acceleration, drag, and the elastic spring force. Now, in this particular case, we can easily write down a differential equation for the position x of this mass because we know that the velocity u is the first time derivative of position, acceleration is the second time derivative of position. Just like that. So we have a second order constant linear ODE. Second order constant coefficients because zeta and mass, spring constant k, and mass are constants. It's a linear ODE. So we all know how to solve this. I still remember this equation in my college physics class where the professor wrote down this equation and wrote down this. Show, simple harmonic oscillator. And I remember saying, that's my name, that's me, I'm Show, I'm right here. So you see two shows, me and here. And I still remember this moment, and I kept thinking, simple harmonic oscillator, SHO. That's like the one time I've seen my name represented in physics. So there it is, my name represented in physics. So now, with this equation, we can write down the states, the dynamics, And let's talk about the measurements in a little bit later. In this particular equation, our states are the position, x, and the velocity, u, which is right here, which is just u. Acceleration is an outcome of this equation, and therefore it's not a state of your system. And you must have solved this simple harmonic oscillator equation in your past classes. It's just a simple pendulum that goes back and forth, but because there's damping, what you see is that the oscillator will go up and down, but slowly dampen because of this viscosity term. So it looks just like this. It just dampens. So you kind of have an intuition of what the solution to this differential equation looks like. We're going to consider this equation in a slightly different context, in the context of observability and embedding. So we can write down the dynamics of our states and how that gets evolved to the next time step by looking at this equation. Let's write it in matrix form. So what we want to do here is to take the time rate of change of our states, which in this case is position and velocity. So what we have is the first term in this column vector is dx dt, so that's the instantaneous speed. And now you have the second derivative of position because the derivative of u is just the first derivative of x with respect to time, so you get a second derivative. And now this we can write as a function of our states in the following way. Just like that. So the first term up here, dx dt, that's the definition of the velocity. And therefore, dx dt is just your velocity. And now d squared x dt squared can be obtained directly from this equation, or this equation up here, right? You have your acceleration is equal to the negative of zeta over m times u minus elastic spring constant k divided by m times the position. So here are your dynamics. And now what you can see is that we can factor out the u and the x and rewrite this as a matrix vector linear algebra form. Just like that. So we can see is that the first entry, 0 times x, 1 times u, that gives you the velocity, the first row inside your dynamics. And the second row is negative k over m times position, that's that term. Negative zeta over m times u, that gives you the other term in the second row. Therefore, you can write this in a matrix times your states z. So what you ultimately have is a linear system where your next state at the next time step is just a matrix A, which is called the state transition matrix, times your states z. So what we have is a dynamics that looks like the time derivative of your state vector z with respect to time is equal to some matrix A, called the state transition matrix, times your states z. Now, this is a very important linear equation that tells us how to map your states z, in this case, position and velocity, from the current time step at t to the next time step at t plus 1. So this is your dynamics. If you know this equation, which we do in our case, we can map our current position and velocity to the next position and velocity. Now, in this particular case, because we're covering observability and embedding, let's suppose that your measurements are only measuring position. So you have a camera, you're taking a picture of this mass and spring, this mass going back and forth, and you're taking instantaneous pictures of this system. That means you don't have a measurement of the velocity, right? If I just hand you a picture of this mass at some time step, all you see is a mass with a spring connected to a wall. You only know its position, x, but you don't know its velocity. It's not like you have a speedometer to check how fast it's going. You don't have that measurement available to you. You only have a measurement of a camera, which can only take pictures, which only has access to position. So your measurement, y, would only be x. You do not have measurements to the velocity, u. So here's a situation where you have a partial measurement of your full states, but not your entire state. Okay, so now your measurement, y, would only be your position, and therefore your measurement matrix would just be a row vector of 1 and 0 dotted into your states, x and u. So clearly you can see if you do a linear algebra calculation, you would pop out the x only. So you only have a measurement of x, but in reality, your dynamics depend on both position and velocity. So let's talk a little bit about observability and how you might be able to just take pictures of position x to discover the whole states, including your velocity. So I've just rewritten the measurements y up here. So it's the same equation that we have over here, just rewrote it over here, because I want to consider one thing. Suppose we were to take a time derivative of your measurements y. So I don't want you to get confused here. Your actual dynamics depends on z, but you don't have access, direct access or measurements of all of your states in z. You only have y. We're going to take a time derivative of your measurements. So in this case, position only. So if you take this time derivative, it'll look like this. Okay, so I've just literally taken a time derivative of this equation up here, where c is just a constant, so it could just pop right outside. This z is your state, so now I have dz dt. That's just direct time derivative of this top equation. But dz dt is just our dynamics, which in this linear case, we have dz dt is equal to the state transition matrix A times this state z. So we can rewrite this in the following way. Just like that. So we now have is dy dt apparently is equal to the measurement matrix C times A times Z. So you can see that my dynamics directly came into play right here. That maps our current states to the next states in time. Now we can write this in vector matrix form once again, like the following. Just like that. So what I've done here is to take the top equation, put it into the top row right here, which is y is equal to c times z. Okay, so just put this directly on top. So c you can put here with x and u, so that's your top entry. And the bottom entry right here, which is your time derivative, I put in the second row, is equal to c times a, which we have right here, times z. So all I've done is to take your measurements of a single picture in time, and the time derivative of that picture is equal to this linear algebra operation on the right-hand side. Now, this term over here on the right is called the observability matrix. The observability matrix, which I've denoted as theta. It's just a matrix that we know the values to because we know C, that's our measurements, and we know A in this case, that is just our state transition matrix from our second order linear constant coefficient ODE. So let's just actually evaluate what this observability matrix looks like for our very simple example. We already know what C is. C in this case is just a row vector of 1 and 0. This second row right here, C dot A, let's work out over there. Okay, I'm just cramming this small little linear algebra matrix product over here on the left-hand side here. We have 1 times 0, so then you don't pick up anything in the first entry. So the first entry here is just a big 0, because once again, 1 times 0 plus 0 times negative k over m is equal to 0. Great. So now the second entry is 1 times 1, so we pick up a 1 there, plus 0 times negative zeta over m. Therefore, we just get 1 right there. So now we can write down our observability matrix, because the first row is just 1, 0. The second row is just 0, 1. Let's write that down. So our observability matrix is just this identity matrix of 1s along the diagonal and 0s on the off diagonal. So this matrix is full column and row rank. In other words, the rows and columns of this matrix are linearly independent. Now, what this means is that we can have a well-defined determinant of this matrix. We can invert it. And so let's think about this for a moment. We have this equation. We have measurements of y, which in this case is just your position x. We don't have measurements of your velocity. So let's write down this with y just replaced with the position x. So we have this equation down here. Now, the left-hand side are your measurements. You've taken pictures of the mass going back and forth. You have access to position, but you also have access to 2 snapshots in time, one now, one time step ago, and therefore you could take a time derivative between your 2 pictures. You could take finite differencing, current position, past position, because you have 2 pictures now. You've embedded one history of your position in the past. You have 2 pictures. Therefore, these measurements you have. So the left-hand side are your data. You have access to those measurements. On the right-hand side, like I said, position you have. So you know what the position is, but you are unmeasured states. And what's connecting your states, including your measured and unmeasured variables, to your measurements is this matrix right here, observability matrix. Now, just from very basic linear algebra, if you can invert this theta over onto the other side, that means that you can uniquely determine all of your states, x and u, from your measurements. And this is the power of embedding. It's telling us that if our observability matrix can be inverted, which it can in this case because it's full column and rank, you can take a determinant, you can invert this matrix, no problem at all. That means if you have your position and a time derivative of your position, then you can measure your velocity even though you never use the speedometer. You could just take pictures and obtain your unmeasured states, in this case of velocity. And when you actually think about it, that kind of makes sense. If I were to take a picture at one time step of this mass at position t and wait a small little time step and take another picture at time t plus 1, then of course you can use those 2 measurements to infer a velocity. And so that exactly checks out, right? If you have some kind of moving object, you take 2 pictures, then you kind of can estimate its velocity. That's what this observability is doing. And the process of taking time history measurements of the position is called embedding. So right now, you've just embedded the measurable quantity, which in this case is position. You've embedded one position at a time in the past, and you were able to estimate an unmeasured state, which in this case is velocity. So it turns out that this can be generalized to any number of unknown states. If this was not just position and velocity, but you had an entire column vector of unmeasured states, what you can do is to just keep taking time derivatives of your measurements, and the deeper you embed your time history of your measured states, you can get deeper and deeper into your unmeasured states inside your whole dynamics, which is a really powerful and really cool trick that you can use, and this is called embedding. For general linear systems, we can write down the following. If your states contain n different variables, temperature, pressure, flow rate, etc., here are your states. Over here are your measurements y. Here are what you have direct access to, measurements of. And everything here, this gigantic matrix on the right-hand side, and this gigantic, ugly matrix on the right-hand side is your observability matrix. We call it theta. So what we find through this linear algebra problem is that for linear dynamics, if we can write down z time derivative is equal to some state transition matrix A times the state z, so that's a linear dynamics, then your observability matrix can be written down in this form. For nonlinear dynamics, you can't write it in this form in general. So for nonlinear dynamics, there's not really a rule that will tell you how many measurements you can make that will uniquely determine all of your unmeasured states. But for linear systems, you are guaranteed that if your observability matrix is full column rank, you can invert it, you can bring this matrix onto the left-hand side. What this tells you is that if you make n measurements of what you have access to, your measurements, that means you can take nth derivative in time of your measurements. Then you uniquely can determine the n moments or n variables inside of your state vector z, even if you do not have direct measurements of a lot of these states. For example, if I only have measurement of one of my variables, right here, z1, it might be, for example, the temperature. And let's suppose that temperature equation through the dynamics are related in a linear fashion to the other unmeasured states in your system. Then you can just take n pictures of your temperature. That way you can get n time derivatives of your temperature measurement. Then you can uniquely determine n variables in your entire state. And that's a very powerful thing, and this is called observability. Even though you have measurements and unmeasured states, those unmeasured states are observable based upon embedding or time delay embedding of one of your measured states. And this is a very important concept. So let's do an example, a different example, not a high school physics example, but one that will actually put this into more context, and I'll actually show you a MATLAB code that will tell you the powers of observability and embedding. Let's do that next. Let's do an example involving chemical reactions. So suppose that you had some beaker with a stirring rod that mixes the fluid around, and there is a chemical reaction happening inside this beaker. And that chemical reaction is the following. It's got three components, component A, B, and C, and there's a first order chemical reaction that goes from A to B, but also reversible from B to A, and also B can go to C and back to B. So the corresponding rate constants are the following. So we have K1 in the forward direction from A to B, K minus 1 in the backwards direction, K2 from B to C, K minus 2 in the reverse direction. Now, we can write down the governing equation for the concentration of A, B, and C as a function of time. It's not a function of space in this problem because we have a well-mixed stirring rod that's mixing things around, and therefore it's only going to be a function of time. And for our first order rate law in every direction, we can write it down cleanly. For example, the time rate of change of the concentration of A, so the bracket A is the concentration of A, in molarity units, for example, is equal to the first term is the rate of loss of A, which is proportional to the rate constant K1. So there's a negative K1 because you're losing A, it's going from A to B, and you have a reversible reaction that depends on the concentration of B, because if your concentration of B is very large, it's going to produce a lot of A. So you're going to have a production of A that's proportional to the concentration of B, and also proportional to the rate constant K negative 1. So we can do a similar thing and write a balance law for B and C as well. It looks just like that. So we have concentration of A, concentration of B, concentration of C. I already went over the conservation of species A. conservation of species B will just look like these 4 terms, because B sits in with 4 arrows. We're going to have 4 components on the right-hand side. How much A is turning to B, how much of B is turning back to A, how much of B is being lost to C, and how much of C is being produced to B. Sounds like a Dr. Seuss riddle puzzle. And component C just has these 2 terms. All right, so now we can write this coupled ODE for A, B, and C in linear algebra matrix form. That will look like the following. It should look like the following. So all I've done is to take these 3 equations that I've bracketed in pink over here on the left and wrote that in matrix form. So first, the time derivative can be popped out. Now I have concentration of A, B, and C that I've wrote down as a column vector is equal to this matrix, which is our state transition matrix, dotted into our state vector A, B, and C. So if you were to check, for example, let's do the second row. So this is d concentration of B, dt, should be equal to K1 times bracket A. There it is. Negative K minus 1 plus K2 times bracket B. That's these 2 terms. And lastly, we have K2 times bracket C right there. So actually, this term looks like it should be minus 2. I think that's correct. I think this should be a minus 2. There we go. I'm glad we checked. We forgot that negative 2. So there we go. That's the matrix that will take the current concentration, project it onto the next time step. So let's make a label for each of these terms. So our dynamics can be written in this linear form, where I have the time derivative of my state vector z is equal to the state transition matrix A dotted into my states. So in this case, we have 3 variables, dependent variables, bracket A, bracket B, bracket C. Those are concentrations of species A, B, and C happening inside of your reactor. Now, let's talk a little bit about measurements, because we have our states, we have our dynamics. The third component is our measurements. Let's write that down. Let's suppose that for whatever reason, inside of a reactor, you only had direct access or direct measurements to the concentration of species A. So you cannot measure B and you cannot measure C directly. Therefore, your measurements Y would just be this observation matrix, C, 1, 0, 0. It's just a row vector dotted into your states of A, B, and C concentration. And therefore, you would just pick out your first entry, which is just your concentration of species A. Now, let's suppose that you have measured the concentration of A as a function of time, and therefore we can set up the observability matrix in the following way. So now our measurements Y and its time derivatives will be equal to this gigantic matrix, which is our observability matrix, dotted into our states A, B, and C. Now, like I said, you do not have measurements of the concentration of B and C, but you might want that as an engineer. You might want your product C to meet your main valuable commodity, but you only have measurements of your reactants A. So the question is, can I just keep measuring my reactants of A only and estimate what my product C may look like? That's what this linear algebra form is showing. And now we can work out the observability matrix for this simple case of the reversible first order chemical reaction, because we now know our C vector in this case is just a row vector of 1, 0, 0. So we have row number 1 here. C dotted into A is just this row vector dotted into this state transition matrix, which came directly from our dynamics. And we can also do this third row as well. And I'm going to show you what the observability matrix looks like in this particular case. It would look something like the following. So we know the rate constants, k1, k minus 1, k2, k minus 2. And you can see here that this is full rank in general. As long as these rate constants are not 0, if they're 0, they'll actually decouple the connection between A and B and C, and therefore if they're decoupled, you can't infer C from A if they're decoupled. So if the rate constants are non-zero, then you have a full rank matrix, which means you have an inverse. You can take this observability matrix, invert it onto the left-hand side, and so you can make a lot of progress. So what we find from this analysis is that because we can invert our observability matrix over onto the left-hand side, as long as we make a measurement of y, which in this case is only our concentration of species A, so we have our reactant concentration at the current time, 1 time step in the past, 2 time steps in the past. So you're able to take 3 measurements of your chemical concentration of your reactants in time. What that means is that you can actually uniquely determine the concentration of B and C that you never even measured to begin with. This is the power of estimation. So let's see all of this in action, because I think it's just such a cool concept that we don't know what B and C are. We don't have access to them experimentally. As an engineer, there are many situations like that where you want to measure B and C, but you can't. But you can measure A, no problem. Let's just measure A in time and do a time embedding of current A, past A, to past A. And then magically, you're able to determine things that you actually never even measured. That's what this is showing us. So let's go over to the MATLAB code, because I wanted to show you this in actual use of measuring concentration of A to determine B and C components as well, which you never measured to begin with. Okay, what we have here is a very simple MATLAB code that will simulate A going to B, going to C, first order reversible chemical reaction. And we're going to try to construct the full state vector using only measurements of A, and using measurements of A to take its time derivatives. So first, I need to specify the rate constants for K1, K minus 1, K2, K minus 2. Those are just arbitrarily determined by me. That will be based upon your chemistry of the rate constants connecting the 3 different chemical species. Now I'm going to time integrate this. Okay, and so I'm going to specify an initial condition of chemical reactant of A set to 1 for initial time. And then first, I'm going to create simulated data sets based upon the solution to this coupled ordinary differential equation. So you can see here, dA is this top equation over here on row number 1. This is the rate equation for species B, species C. And then here, I'm just time integrating forwards. So we have the chemical concentration of A at the next time step, I plus 1, is the current time step concentration plus the differential times the small delta time step, delta t. Okay, so now, like I said, we only have measurements of A. So this is the actual full dynamics that will allow us to compare it with the actual prediction based upon our observability. But we have to remember now, at this point, we only have measurements of A. So what we can do is to take derivatives of species A based upon our measurements. So at the end of this simulation, we're going to have a time history of all of our chemical species A only. That's all we have access to at this point. Now we're going to take that time history of the chemical species A, take the first derivative, which is what I'm doing here. This is dA dt. This is taking another time derivative. So this is a second time derivative of bracket A. Now what we're going to do is to first construct the state transition matrix A. So that's this matrix right here on the board. I'm constructing this 3 by 3 matrix right here. So you can see negative K1, K minus 1, and so forth. The C matrix is our measurement matrix. That's this over here, up here on the top right, where I have a measurement matrix that tells us I only have access to the chemical species A. Therefore, you can see here that I have a row vector of 1, 0, 0. Now, next, I'm constructing the observability matrix. That's this theta matrix right here. We have C, C.A, C.A.A. So we're going to construct this observability matrix over here in code, which is exactly what I'm doing here. So I have the C matrix, C.A, C.A.A. Now, what I'm doing next is to invert that observability matrix. So I'm on the board, I'm taking this observability matrix, inverting that, putting it over on the left-hand side, because I want to measure my unknowns on the right-hand side. It's literally just a linear algebra operation. So now what I'm doing here is constructing my measurements y. So this is a vector of my current state, the derivative, the second derivative. And over here, I'm just literally doing inverse of my observability matrix dotted into my measurements. And that's it. So x hat contains, presumably, concentration of A, concentration of B, concentration of C. And so I'm just going to load measurement of A, or the estimation of A, from the second entry, and the estimation of C from the third entry of this backslash operator, essentially. We're inverting it, we're doing least squares, we're obtaining the degrees of freedom of A, B, and C. And after that, I'm just plotting them down here and comparing the true results, which came from the simulated data set that we've obtained here for B and C, and comparing it with our observability method of just directly constructing this matrix, inverting it, and obtaining our final answer. Okay, so I'm going to execute this, and this is what we get. So we find here is 3 plots. On the left, this is our chemical concentration of species A, initial condition of 1 as a function of time, species B plotted in the middle panel as a function of time, and concentration of species C plotted as a function of time as well. Now, far left, for species A, this is our exact solution. Those are our raw measurements. We measured that. Again, we have direct measurements of species A. That's all we know. For B, what I'm showing you here is, first of all, the dashed line is the true simulated data set. That came from solving this ODE. We have a time history of species B. That's what's plotted in the dashed black line. Now, this red curve right here that smack-on overlays on top of the true set came from this observability calculation. Once again, I only measured A. The concentration of A, embedded that in time. So I measured my current A, past A, 2 past A's, taken the observability matrix, inverted that, and now we have an estimation of the chemical species B, and that's what's plotted in red. The same thing for species C. Dashed black line is a true simulated data set. The green curve is the reconstructed C based upon our estimation from this observability matrix. And you can see it is smack on, gives us the exact result. So it turns out that the observability and embedding is such a powerful tool for us as an engineer. You don't need to measure all the states in your system. If you have very good measurements of one of your states, and you know the dynamics and how it couples to the other states, you can just take your measurements of the state that you know, the measured states, to estimate what your unmeasured hidden variables are. Now, there are some pitfalls to this approach though. despite everything here looking like it's working so well, there are some things you need to watch out for. For example, let's add noise. As an experimentalist, you know there's always going to be noise in any experimental set or any particle-based simulation or any real-life application. You're always going to have noise. So what I've done here is to generate the exact same system, except right here, I've added 1% Gaussian noise. So I've taken the concentration of species A, added some noise to that, and repeated the exact same thing. If there's a little bit of noise on species A, it turns out the method performs extremely poorly. So first, over here on the left, we have species A. The dashed black line is the clean data set with no noise. If you add 1% Gaussian noise, you can see this blue wiggly squiggly line. That's the noisy measurement of A. And you can imagine that you can have noise in your actual system, but you can have noise in your measurement. If you have some thermocouple that's measuring temperature, or some kind of function generator or oscilloscope or something that's receiving signal, it's going to have noise in the actual measurement tool that you're using. And therefore, there are multiple different ways in which noise can contaminate your signal. So this blue squiggly line might be your measurement of your chemical concentration of species A. But then if you try to embed, just like how I told you, by taking derivatives of these squiggly lines, you can tell that there's going to be a disaster. Because now we're taking time derivatives. So let's just suppose that little point right there is our current time. The next time is there, next time is there. So you're going to embed these 3 points into the measurement vector, and you're taking derivatives of this. So this is going to be strongly negative, and then boom, strongly positive. So your measurement vector over here on the left-hand side of the board, this dy dt is going to be a crazy function as you slide forward in time, because small little noises in your measurement is going to amplify like crazy in your derivative. This is the same thing that we talked about with that sparse regression, where if you have a little bit of noise, it can really throw off your fits. Same thing here. So as you might be able to expect, your estimation of B is just wild. I mean, it's giving you negative concentrations, which is aphysical. It doesn't even make any sense. I can't even see the true dashed line because it's hidden inside of here somewhere. Same with concentration of B. It's even worse. So your measurement estimation of C is even worse because you're taking a second time derivative, which is a curvature, which is even more penalizing for noise. And therefore you can see that the y-axis is going into the thousands. So this is like very, very wrong. So like I said in the past lectures, there are some tricks you can play. For example, you can take this noisy data and smooth it out a little bit. And that's what I've done here next. We're going to take that same added noise data set, but used a smoothed version of that. So what I've done here is added noise as usual, but I'm going to do a spline smoothing on that noisy data set. So that's what I'm doing here in this operation. But below that, everything is the same. I'm going to generate my state transition matrix, my observability matrix, and so forth. I'm going to invert and then plot the result. So now if I evaluate this smoothed version, this is what we get. So let's just go through each of these plots. So over here on the left-hand side, we have the concentration of A. The black is the true clean data set. The blue was the noisy one that I showed you earlier. A is the smoothed version of that noisy data set from the blue over to the red. So you can see it's a little bit cleaner. The derivatives are, as you can imagine, are going to be a little bit cleaner because we've interpolated a curve through that noisy data set. And over here in the middle panel, we have the concentration of B. The black line is the true data set in the absence of noise. And you can see that the reconstructed B does a better job. It's at least capturing the overall trend. It's not perfect because you're still going to get a little bit of noise that contaminates into your smooth data set. So your time derivatives are still not going to be perfectly smooth, and that's why it's going to be a little bit jagged, but it's not that bad anymore. And the same with the data set for concentration C. So the black dashed line is the concentration for the true clean data set. The estimation based on green, it's a little bit noisier at early times, which is, I guess, kind of expected because there's a lot of transient dynamics happening at early time. So even a little bit of noise causes huge errors when your concentration on average is also rapidly changing in time. But otherwise, it's changing more modestly at later times, and the smoothened data set captures the trends a little bit better. All right, so here was the second example where now we have a reversible chemical reaction. And it just turns out that if you make a measurement of A only, you can take the observability, invert that, and actually be able to estimate variables that you actually never measured directly. So it's a very powerful tool for us to be aware of, this concept of embedding. Of course, with noise, you have to be careful, just like I showed you, but still it's a very powerful technique. Now, to end off with this lecture on embedding and observability, let me show you a practical research example where my lab has used embedding and observability to make progress in answering a research question. Let's do that next. Here is a movie of a bacterial colony gliding along a petri dish. Each little tiny little speck, this little grain that you see in this movie, is a tiny microscopic organism. And this bacteria is able to glide along a substrate. And because they interact with their neighbors, they're sometimes able to align with each other and form these beautiful patterns that show up along the front of this migrating colony. Now, if you were to take this bacteria under much more dilute conditions and watch them just swim around inside of a fluid, it would look something more like this. This is called a run and tumble motion, where you have bacteria, they use their flagella, which are appendages along their body, that allow them to propel along a fluid, and after some time, they get to reorient by unbundling their flagella and move off along a new direction. Now, if I wanted to solve the dynamics of how these little constituents move along inside of a fluid, there is a function that I'm going to call P that describes how they move, where, in which orientation, at what time they are located inside this fluid. Now, it depends on the position of that constituent at some position X and their orientation theta. That tells you which direction they're pointing in inside of that fluid. It's also a function of time. Now, the governing equation that tells you how this function evolves as a function of position, orientation, and time looks like this equation. It's a convection diffusion equation. It's got an accumulation term on the left-hand side as usual. It's got a convection term due to the fact that they're swimming. As they swim, it's like a convective motion as they go from one place to another. That's showing up here on the second term. And lastly, we have diffusion term, a Laplacian term, both in position and in angle. You can imagine they undergo Brownian motion along position, so there's some stochasticity associated with where they get bumped around due to the solvents bombarding into their body. But they can also turn and reorient and move off in a different direction due to solvents bombarding along their body. So you have thermal diffusion that's happening both along translational space and also in orientational angular space. Now, you could solve this partial differential equation, but it's a little bit annoying to solve because this function is a function of position, angle, and time. That's a very high dimensional space that you're dealing with. So what people in the community often do, not just for these swimming little microorganisms, but a lot of materials in general that are composed of individual constituents, what we often do is to break down this equation into what are called moments. So what we do is we take this whole distribution function, which is a function of position and orientation, we integrate this function over all orientations theta. So the result of that integral will only depend on position and time. That's what's called the density. So the density tells you how dense is my constituent inside my fluid at a particular position X and time. Once again, you've allowed this constituent to sample all orientations inside the fluid, so it's no longer a function of angle. It's only a function of where they are located along translation space, x, and time. Now you could write an equation for this density field, similar to the evolution of a density field that you might learn in your undergraduate engineering classes. And it would look something like this. It would look like the time rate of change of a density, so this is like an accumulation term. This is kind of like your usual fixed second law term, your heat equation or your diffusion equation. And this term right here is your diffusion term. So this term plus the first term on the left would give you your usual heat equation or your diffusion equation. Except, of course, because they're able to convect and swim along a direction, you're going to get a second term here that comes directly from their ability to swim. But if you notice, if I were to integrate this term over all orientations theta, this q vector just tells you which direction they're pointing in as a vector. So it's cosine theta and sine theta. It's a 2D vector in 2 dimensions. There's a 3D analog, but for simplicity, I've just stated that for 2D. But you get another term here that depends on one moment below, which is called the polar order. So this polar order is defined as this distribution multiplied against the orientation that are pointing in, and then you average and you integrate from 0 to 2 pi. So that tells you on average which direction they're pointing in. You saw in the previous slide, the movie showed that all the bacteria were drifting and moving along one direction. That's polar order. They have polarity in the direction that they're fluxing towards. So ideally, I like to solve an equation just for the density, but then unfortunately, it's coupled to which direction they're pointing in. That kind of makes sense because if a crowd is going from left to right, of course, the density is also going to increase from left to right. So it kind of makes sense that if I want to solve an equation for the density, it's going to depend on which direction they're collectively moving in. But I can write down a separate equation for collectively which direction they're moving in, the polar order, which looks like this. So this equation comes directly from the original equation, where you multiply this equation by the orientation, and then you average, and you get this equation right here. But of course, unfortunately, the convective term right here is going to then couple to one moment lower, which is called the pneumatic order. This tells you which direction are the constituents aligned relative to their neighbors. So it tells you how they're aligned relative to their neighbors. So as you can see, this next equation for the pneumatic order will couple to one moment below, called the skew field. So you get an infinite hierarchy of partial differential equations that are coupled to each other. The density depends on which direction they're pointing in. Which direction they're pointing in depends on how they're aligned relative to their neighbors, and so on. So at the benefit of going from a partial differential equation and removing 1 degree of freedom of theta came at the cost of having an infinite hierarchy of coupled partial differential equations. Now, you might wonder, how does this even help you? We'll get to that in a little bit. But oftentimes in an experiment, for example, an experiment that our lab might conduct, we take microscopy images of our complex materials. It might be a suspension containing microscopic organisms. It might be a hydrogel polymer solution containing microscopic little tiny polymers present inside of our fluid. In various situations, we're going to have an image that might look something like this. So this is a picture, in this case, of microscopic organisms that are fluorescently labeled. And all you see are small little tiny dots inside of your image. So unfortunately, we have access to the density, but not all these higher order moments. You can see based on the image, based on the dots, you know the density, right? These bacteria are small compared to the pixel size, and therefore we have an estimate of, okay, how dense are they located as a function of position and time, right? In the middle, they're more densely situated compared to the edges of the picture. So you can kind of have an estimate of a density, how many particles or how many objects there are inside your fluid as a function of position and time. But I can't see which direction they're pointing in on a microscopic scale because they're tiny. All I see are little pixelated dots along my screen. So I have access to the density and density only. But if I want to solve the equation for density, it's not completely closed because I don't know what this m is. And to figure out this m, I need to do these higher order moments. And then besides, I don't even have experimental measurements of m. So here is a question. Can I learn the governing equations using only one measurable quantity? So this is where it gets into everything we've been talking about so far today about observability and embedding. Here is a real situation where this is a pressing issue in the community. We only have direct measurements of one variable, but that one variable depends on a bunch of other hidden states that we don't directly have measurements of. So, can I just take a bunch of pictures, a bunch of measurements of my density field and get by with coming up with a model? That's what I like to talk about here, and it's completely relevant to what we talked about today. So, our states are all the variables, density, polar order, pneumatic order, all the higher order moments listed as a column vector as shown here. Now, the dynamics, you can rewrite the equations I had on the previous screen of the equation for density, equation for polar order, and keep going on. And it turns out that it's a linear system. For a dilute suspension of these microscopic objects, it is a linear problem. Once they start interacting and colliding and start doing more complicated things, it turns into a nonlinear PDE. But for a single dilute entity in a fluid, it's a linear equation. And therefore, you can write the equation as the time derivative of your states. I called it z earlier. I'm calling it x now. I think you can make that conversion inside your head. So time derivative of all of my states is equal to the state transition matrix A. Those are all the convection, diffusion, time derivative, everything that, well, the time derivative is outside, but all the convection and diffusion operators are inside of A, acting along all of your state vector. Now, unfortunately, like I said, we only have measurements y, which is only the first entry inside that state vector, which is density. So we have a row vector of c, which is 1, 0, 0, 0, 0, 0, 0, 0, all the way, because I only see density. So you take this C matrix, or in this case a row vector, dot it into the full state column vector, and you pick out only the density, right? Because you do this linear algebra operation of C multiplied against X, and then you only pick out this first element of N, and that's all we see. So my measurements Y contain only the density. Okay, so here are the dynamics, and here are the measurements. Now let's think about this in the context of what we talked about today. So I have my measurements y, which is equal to the output matrix C times our state vector. I could take a time derivative of y. My measurements looks like this. But this, I could use our governing equation. That's just equal to A dotted into the state vector. And therefore, we get this expression on the right-hand side. I could take another derivative of my measurements. You get another A to pop out. Looks like this guy. And you can keep going, like I just showed you earlier. And you can put it into a gigantic matrix form as shown here. So on the first column on the left, here are all of your measurements and its time derivatives. This gigantic matrix here is the observability matrix. That's completely known because we know our A matrix, we know our C matrix. And lastly, this right-hand side term is your entire state vector. But like I said, you only have measurements of your density. I only have pictures of these speckled little dots in my experiments. So I have access to my density only, but I don't know which direction they're pointing in, how they're aligned relative to the neighbors. I don't know any of these terms from the second row all the way to the highest order moment we can consider. But if you can now know from observing this lecture, is that if I can make measurements of my density in time, so take multiple pictures of my sample in time, I can approximate the time derivative of density, the curvature time of density, and so on. I can take k derivatives of my density with taking k pictures, right? I can approximate a derivative by taking k pictures, the kth derivative. That means that I can invert this observability matrix onto the left-hand side. This entire left-hand column is your measurement that we can take directly from a microscopy. And then that means that we have all of our states that we can infer and estimate. This is consistent with everything I've been covering so far today about making a measurement of one variable only, taking a bunch of measurements in time, embedding that to discover all the hidden states and unmeasured states inside your system. And this is a very powerful demonstration of how we can use embedding to help develop models and estimate unknown properties inside of a material. And now if you think about this more generally, it kind of makes sense that if I have a bunch of agents or constituents or objects or any particle constituent inside of a system or a material, if I take one snapshot, like the one you see here, a bunch of people crossing a famous crosswalk, you can get a direct measurement of the density. But if I take one more picture, so I'm going to move one time step, so I've just moved one time step from here to there. I've taken two pictures, two successive pictures. But now, because I've taken two pictures, you can take a time step forward and you can see which direction they're pointing in. That makes sense. You can now see which direction the agents are going in. That kind of makes sense. And if you take another picture, you can tell how the agents are oriented relative to their neighbors. And now if you take a movie, which is just a collection of individual pictures, you can get all the moments all the time by taking a sliding window in time. So you can estimate all of these hidden states inside of your system just by taking one measurement of the density many times in time. And by doing that, you can come up with an equation that will tell you how the density field slowly evolves as a function of position and time through an evolution equation that looks just like the normal diffusion equation with a convection term right here. Now, the main piece of heavy lifting comes down to how do you figure out what this convection term is and how do you develop a model for that term is. And this is actually what our lab is doing right now. How do you take experimental simulation measurements of an observable quantity like density, and how do you develop an equation for that quantity by closing the equation for the convective term? And it turns out that using the time history of the density measurement really helps us out and helps us narrow down what would be a good model to use for this convective term and what closure we can use for that term. So it turns out that, again, there are various different ways to model this convective term. And right now we're pursuing analytical techniques, semi-analytical techniques, as well as fully numerical techniques as well. So in any case, that is all I wanted to cover. I wanted to end with an actual practical concrete example of how a researcher could use observability and embedding to their advantage by taking only a single variable, measuring that very precisely to discover all the hidden states inside your system to develop a model. With that, I hope you have a fantastic day, and I will see you next time. Bye.